Okay guys, for LP2 you'll have done some expansions of functions like this. You don't need to use Pascal's triangle to find these coefficients because they've given you the expression or a general formula that allows you to find using combinations. The reason for the combinations is basically working your way through Pascal's triangle. So you can use this to expand a function completely. It's got a problem though, in that because this involves factorial, we can only do factorials of positive numbers, positive integers. So it causes a problem that we can't expand things like a plus b to the half. It only works on integers, on strictly positive integers. So it's actually been attributed to Newton, this thing. What Newton did was he took the expression and he said, well, what happens if I want to change these to non-integer numbers? And what we need to realise before we start on this is we need to work out some patterns that happen with our factorials. So the number factorial, a number to a factorial, if you know the factorial of the number before it, you can calculate this one just by multiplying by n. Or if you know the 1, 2 before it, so what's happening is, if you work your way backwards, we can get a bit which is a normal number, doesn't involve the factorial itself, and the part that contains the factorial. So the factorial part is the part that actually leads to only integers. These other ends can be removed. So what Newton apparently did is he started with a simplified version of this, and the simplified version is the version you will need. And the simplified version is, he began with an expression which was, what happens if I do 1 plus x to the power of n? Now this x part in a minute we're going to be talking about that being a function, and why can this work, and when does this work? Because there are limits. So there are cautions about what things can be for the x here. So let's write out fully what this could mean. Take the first term, 1 to the power of n, well, it's always going to give me 1. Then put in the next step. The next step is n over 1, which is n factorial over r in this case is 1 factorial, n minus 1 factorial. And that's a to the n minus 1, which is 1, so that's 1 to the n minus 1. We'll write it out properly still first. And we've now got our x term, our first x term, with a 1. Let's do the next term, n factorial over, now we've got r is now 2, so we do n minus 2 factorial, and we've got 1, n minus 1, got x squared. And let's keep going a little bit further. We go n factorial over 3 factorial, n minus 3 factorial, 1 to the n minus, that should be 2, not 1, 3, times x cubed. And I could keep going with this forever. Okay. And there's a point about this forever when we come down to dealing with non-integer values. Because the reason this actually stops when you do this is eventually when we're doing factorials, you're doing 0 factorial. And that drops to 1, and you're going to multiply by something which is 0. So it disappears. So eventually this always terminates. and this version it terminates. So this version, this is what Newton realised. Let's come back. Let's go through and do these substitutions. So instead of n factorial, I've now got n minus 1 factorial. I've got n minus 1, n minus 2 factorial. And n minus 1, n minus 2, n minus 3 factorial. And what you should recognise from these is these factorial parts cancel. So we're going to cancel the n minus 1 factorials, the n minus 2 factorials, the n minus 3 factorials. And the resulting expression, and I'm going to do some simplifying along the way. So 1 to the n is always 1, so the only place I need to write it is in this first term. In the second term, I've got n factorial. Oh, sorry, not n factorial, not n, just the n part. So the n minus 1 factorial over the n minus 1 left me with the n. This becomes 1, and we've got x. Add the next part. We've got n minus 1 over just 2 factorial. 1 goes to the power of 1, so 1 goes to 1, don't need it, x squared. And we can keep going with our expression. Let's do it with one more. Cancel the n cubes, so we've got n minus 1, n minus 2, x cubed, all over 3 factorial. And this continues going for each value, so that we've got n minus 1, keep going all the way up to n minus whatever precision we are at. So that's doing each of these brackets, all of these brackets multiplied. The value we went up to, our factorial, and x to the power of r. Now we're not going to set stops there yet. There's a reason for this. But this is the formula given in the book. This formula is actually given to you in the book, just underneath the previous one. So this is actually in the formula booklet. It's actually on the P2 page, along with the previous version. Okay, so it's actually given to you. They haven't gone to this third term, they've given you just that. But there's a little caveat here. And there's a reason for this. First thing to realise is, at no point, if n is not an integer, is either less than 0, this series of products, we're going to get n minus 1, then we're going to get minus 1 times minus 2, and then on the third one we're going to get minus 1 times minus 2 times minus 3, minus 1. We're never going to get to a point like you do with the binomial above, this top one. In this one, eventually you get to the point where the binomials cancel out to 0, and you can't actually do anything. So, but this one doesn't. This one continues forever. So this, for negative values of n, for negative powers, it continues forever. And the same thing if n is not an integer. So if you say you had 1/3, you get 1/3 times minus 2/3, and then 1/3 times minus 2/3 times minus 5/3. It will keep going. It never gets to 0. So this is why the n value here, first of all, this is why it continues. This is an infinite series. And that causes a problem. The second problem is that we can only actually get this to be a reasonable approximation, the 1 is fixed, so that 1 is okay. But what we need is each of these x values, we want these to be getting smaller. So for a good approximation, x needs to be greater than x squared, greater than x cubed, greater than x to the 4, greater than x to the 5, and I'm actually talking about the modulus of x in each of these cases. So we're actually saying that the more terms you put on, the smaller the value becomes. So each term gets smaller, or it converges. To 0. Okay, and there's a couple of things that help us do that. Number one is, as this is going up in powers, the increasing value on the numerator, because this is going up by multiplying by another number, is more than knocked out by the factorial on the bottom. So this stuff should be helping us, and then making sure that this never actually blows up means we get converged to 0. And that means that the modulus of x needs to be less than 1. If it's less than 1, you've got things like 0.9, square at 0.81, square again 0.729. So they would gradually they would converge. The x terms are getting smaller and smaller and smaller. Okay, so that's the theory. It explains why we need the values, and it will explain what's happening with the numbers going on. Now, this x function doesn't just have to be x. So I'm going to skip the early example and let's give you one of the later ones, and I think I'll do example 3. So example 3, we need to show that we need to do an expansion of, and they will often ask you to expand only to a certain point. So we're asked to expand to the x cubed term. Now sometimes you might have to go a bit further, because some of the functions have different orders of power going on. So if you were asked to expand to a term 3, and you had a function which is being multiplied by another function, you may need to find more terms than the x cubed directly. It's what their answer needs to be. So, and this is actually a useful function, because if you rearrange it, it's actually trying to find what is the actual solution to this would be to say that you want root 2. The answer to this, we would like it to be a value of root 2. But let's go in and see what happens when we do this first part. For part A, we need our algorithm from above. So this is in the form of the booklet, so I'm going to use it. And we need to write this in an index form. So the index form has, we've got 1 minus 2x to the half. We also need to realise that the x in there, so in this function here, that x is minus 2x in my expression. So let's expand it. We get a 1 plus, we get n is a half, times our x, which is minus 2x. That's my first term. Second term is a half, because of the first one. N at minus 1, so that's going to be minus 1 half multiplied, all over 2 factorial. So let's put the 2 factorial as a fraction. That's actually 2. X squared. And this is where you need to be careful that you know what the function is. So instead of x, we're writing minus 2x. So it goes in the bracket and it is squared. Do one more, because we want the cubed term. So we've got n minus 1
n minus 2 over 3 factorial, which is the denominator, and then minus 2x cubed. And we show it continues. So I'll just go back, put some little notes on what these things are. Sorry if there's a bit of a jump. So the half is the n, minus 2x is n. What I need to do now is simplify all of these, n minus 1, n minus 1, n minus 2. So that's all matching up. The red stuff matches up to these formulae. Okay? So we now put in our values and simplify. So we get 1 minus x minus x squared over minus 2 squared is 4, so it's going to cancel with both of them. Little note on that. Okay, so this is 4x squared at the top there. This one's going to be minus 8x cubed. Don't forget about these powers. Power goes on the number and it changes the signs as well. So I've now got 4 cancels with these two. I've got a negative x squared over 2 in the factorial. Subtract again. I've got 8 cancels with these. It's a negative 8. The minus 1 minus 3 positive negative. So we've got a negative 8x cubed over 8 is 8 over 3 cubed, which is, is x cubed, sorry. And that's over so we cancel the 6's with the 3 cancels there, so we've got a half as well. So it's going to continue in a similar manner. And it'll keep going. Start B, we should really say when it's valid for. So we're valid if, and again, this x is minus 2x. Its sign is less than 1. If you take these around, it's valid if, take the sign off, so the modulus gets rid of that sign, divide through by 2, modulus of x is less than 1/2. If this value is any bigger than that, it will blow up and our approximation will not work. So this will lead to valid approximations. Okay. They say using that number, see if we can get an estimate for the square root of 2. Now, rather than directly answering their question, let's just put the numerical parts in first. So if we say x equals 0.01, we get an expression which is 1 minus 2 times 0.01 all square rooted. And that is equal to, or approximately equal to, the values going into here. So 1 minus 0.01 minus 0.0001 over 2 minus 0.0001 over 2 again. And this will, notice these are getting smaller, so this continues forever and converges. That's what allows me to get this approximate value. And they calculated out that the right hand side comes to 0.9899495. And this side is the square root of 0.98. Now there's some manipulation to go on and play about with so that we can get this into the form they would like. What they're trying to find is they want to find the square root of 2 as an approximation. So we look at this side where we've got the actual values, and we can represent that as the square root of 100 minus 2 lots of 49, 0.49, all divided by 100. And it's equivalent, still equivalent to the same number. So what we can do now is, if we take out the number 98, and 0.02 is just 0.98. Yeah, I don't know where that 100 came from, that's why. That 100's in the wrong place. So what they're doing is they're now saying we want to deal with this in terms of things we can multiply, or things we can square root. So we can take out of this 7 over 10 times the square root of 2 which is approximately equal to the value on the right. So we rearrange this to make the square root of 2, and now we can say the square root of 2 is approximately equal to 10 over 7 multiplied by 0.9899495, which is approximately 1.41421357 And I'm not so sure if it's still true. These sort of approximations were very big money at one time for calculator manufacturers to be able to do roots and powers of numbers relatively quickly and relatively straightforwardly. They had algorithms for doing this exact problem. Okay, so there are patterns in this that we use and can earn big monies. Okay, so that's what this can be used for. If you go to PowerPoints, successful to go to the right sort of number of terms, you can be extremely accurate in your values. So that's the first start on using these values. I might put up another video for example 5, but that might be tomorrow. Okay.